Okay, so we are doing this collisions lab, and we have just done some experiments where we applied a force to a cart that's resting on this dynamics track, and we're using the motion detector to determine its position as a function of time. So what I'm showing you here is, on the left-hand side of my screen, is a plot of the location of this cart as a function of time. You can see before the force is applied, the position is constant right here at about between 1.4 and 1.3 meters, and then I apply a force and suddenly its position begins changing. That is, it starts approaching the motion detector. And that's because, of course, I'm applying zero force to it at first, and then I apply a force to it, and then I release my finger and there's no more force being applied. So this force acting over this time interval between about 1.2 and 1.4 seconds causes it to acquire a velocity. So what I'm going to do is I'm going to select some section of the data over here, and I am going to do a linear fit to the data. Okay, so that tells you that its position as a function of time is shown here, and its slope is just about 0. So the slope is the velocity. So the initial speed of the cart is about equal to 0 meters per second. That's the slope of the position versus time. Okay, and then what I'm going to do is in this region over here, after I have applied this force, I'm going to do another linear fit. Okay, so I'm doing a straight line fit to my data, and the slope, so that is the final speed, that is the speed after I applied the force, is negative 0.4815 meters per second. So the final is 0.4815 meters per second. So in other words, the momentum initial is equal to 0, and the momentum final is equal to the mass of the cart times the final velocity, and the final velocity was 0.4815 meters per second. So I'll take this, I'll plug it in right there, and using the mass of the cart, which I'll have to mass the cart, I can find the final momentum. Now the question that we're asking here is, here's my question, does Newton's second law describe what's going on? What's happening? And what I can do is I can use the change in momentum. Tell you what, I'll write this as the derivative dp dt, the rate of change of momentum is equal to the force. Again, if I integrate both sides, that will give me my initial momentum. The final momentum is equal to the integral of force over time from the initial time to the final time. And this will give me the change in momentum, final momentum minus initial momentum, should be equal to the force integrated over time, t initial to t final. The change in momentum I'll just get from so this right here, the change in momentum will just be from the initial momentum and the final momentum. And this right here, well, what I can do is I can integrate from the initial time to the final time. That means the time during which this force is being applied. So about from here to here, let's go ahead and integrate that. And voila, I get the integral of the force. So this right here, the integral of the force over time, that's the area under that curve. The integral of the force is equal to 0.6061 newtons per second. So I'll put a minus sign there, but the minus sign shouldn't really matter that much. It's just a result. It's a consequence of the fact that the force sensor is, when you apply a force, it's calling that a negative force when it's being compressed. But that negative sign doesn't really matter. What we're really interested in is whether or not 0.6061 newtons per second, but newtons times second is the total change in momentum. So I'll let you go ahead and do that analysis.